So what is it we are supposed to find out from this particular problem? So you have been asked to calculate no load voltage gain and output voltage, okay, of the amplifier. Now, to find the output voltage, you should have the input voltage. So here you can clearly observe that the input voltage is given as 25 microvolt. Okay, so that's your first part. In the second part, you need to calculate overall voltage gain if a 10 kilo ohm load is applied across the second stage. Okay, what if there is a 10 kilo ohm load present across the output of the second stage? Okay, and the third one is the input impedance of first stage and the output impedance of the second stage. All right, so that's all you have to find out. Okay, so what I have done is to solve this particular problem, I have written a two-step algorithm. Okay, the first step is to construct RE model, okay, stage-wise, and second step is to find out Z in, Z naught of respective stages. So that's how we basically solve this particular problem. Remember one thing, what I have done over here is I have considered the RE model approach, but in exam, instead of RE model, you can also be asked to do it on the basis of approximate hybrid model. Okay, the concept remains the same. Wherever you have beta RE, you are going to replace it with HIE, so on and so forth. All right, fine. So let's get into the problem. All right, so we have two stages, right? Anyhow, I have already colored the stage one. So what I have done, I have drawn the RE model of first stage, okay, which I have highlighted with the yellow color, and the uncolored region, meant for the RE model of second stage. All right, so pretty simple. The transistor Q1 is being replaced with the RE model, that is beta RE being the input impedance of the transistor, and this is beta IB, okay, where IB is the base current of first transistor. Okay, now if you observe carefully, this is your C1. Okay, let me just rewrite it as C1. So C1 is connected to B1 through the coupling capacitor C01. So for AC analysis, C0 or the capacitor is considered as a short circuit. So you can clearly observe that C1 is directly connected to B1, where B1 being the base terminal of second stage. All right, and again you will have the RE model of second stage, okay, which is consisting of beta RE and beta times IB. Okay, IB. So what I will do, let me consider this as IB2, just to distinguish the two IBs. Okay, so that's your RE model of second stage. Okay, along with the RE model, you will have to consider the respective resistances. If you look at the circuit closely, basically we have identical stage 1 and stage 2 elements, right? In stage 1, R1 and R2 is 15 kilo ohm and 4.7 kilo ohm respectively. So in stage 2, you have once again 15 kilo ohm and 4.7 kilo ohm respectively. Okay, so you know that biasing resistors are going to occupy a path which is parallel to beta RE path in case of bypass capacitor circuit, right? So you have 15 kilo ohm coming in parallel with 4.7 kilo ohm on the input side, and on the output side, okay, you have collector resistor 2.2 kilo ohm coming across the collector to ground path. Okay, so there we are, 2.2 kilo ohm. Okay, so similarly, you can replicate the same, the position of resistors in the second stage as well. Okay, so that will give you the overall RE model. Okay, so this is our overall RE model. Okay, so once you are done with the overall RE model, let us get into the problem solving. Okay, now you need to have beta RE value. Okay, what is beta RA value? We don't have a straightforward, what you say, data which talks about beta RA. Okay, so beta RA you need to find using DC biasing. Okay, DC biasing. Again, the repetition of module 2 concepts. All right, so first you find out RE. You know that RE is 26 millivolt divided by IE, where IE is equal to, okay, IE is equal to, it's a voltage divided bias circuit, hence IE is VTH minus VB divided by RTH plus 1 plus beta times RE. So this is how you can calculate IE. Okay. So this is IB. I'm so sorry. This is IB. Okay. Once IB is known, you can calculate IE. Okay. But what is VTH? VTH is VCC into R2 divided by R1 plus R2. Okay. So VCC is 20 volts, which is given. Okay, let me show you. VCC is 20 volts, and each transistor is having beta or HFE value of 200. So let's keep that in mind as well. So R2. So R2 is 4.7 kilo divided by R1 plus R2, 15K plus 4.7K. Okay. Can anyone tell me how much you will get VTH as? 4.77. Did anyone get it? Pratibha, did you get it?
So doing, sir.
Okay, okay.
Yes, sir.
Okay, all right. So once RTH is found, VTH is found, you can find out RTH. So RTH is nothing but parallel combination of R1 and R2. R1 into R2 divided by R1 plus R2. 4.7 into 15 into 10 to the power 6, because 10 to the power 3 into 10 to the power 3 you will get, that is going to be a mega. Okay, and in the denominator you will have 15 plus 4.7 into 10 to the power 3. Okay, so you should have a value which is less than 4.7 kilo. Okay, I have already calculated, so let me just write the answers. 3.578. If you don't get the similar answers, you can bring that into my notice. Okay, fine. So VTH is being found and RTH is being found. So you can find out IB. Okay, so VTH 4.77 minus VBE. Given you take the given value. If not given, always assume it as silicon transistor. Okay. 0.7 divided by RTH, that is 3.578 kilo plus 1 plus 200 into RE, right? So what's the value of RE? Is 1 kilo into 1 into 10 to the power 3. Okay. So how much you'll get IB as? And then IE. IE is 1 plus beta times IB. Okay, so just substitute and let me know the value of IB.
19.8 microamperes.
Right, 19.89 microamperes. That's correct. All right, so IB is 19.89 microampere. So IE going to be 201 times 19.89 microamperes. That is about 4 milliampere, because it is correct now. You'll get it close to 4 milliampere, right? Just approximating. It is 3.997, so I can take it as 4 milliamperes. All right, so that is your IE. Therefore, you can find out the RE value now. So RE is 26 milli divided by IE, or 26 milli divided by 4 milli. Okay, so that will give you an RE value of 6.5 ohms. Okay, so that's your RE. Therefore, beta RE, okay, is equal to 200 times RE value. So that is going to be 1,300 ohms, or 1.3 kilo ohm. Okay, kilo ohm. Once beta RE is found, okay, you can substitute that value in your circuit diagram. So this is 1.3 kilo ohm, and in the second stage also you will have 1.3 kilo ohm, because both the stages are identical to each other. Hence, all you need to do is calculate the beta RE value only once. Okay, fine. Now let us calculate the no load voltage gain, okay, and the output voltage of the transistor. Okay, so to find the no load voltage gain, what we will do is we will define the individual gains. Okay, define AV1 is equal to, loaded gain of stage 1. Okay, and let us take AV2 as loaded gain of stage 2. Okay, and let us define AV1. Okay, now AV1 is normally taken as, you know that kind of Z0 divided by RE. Okay, so this is from voltage divider bias AC amplifier analysis. AC amplifier analysis, in which you have found that AV is equal to minus RC parallel with RL divided by RE. I hope you remember this particular equation. So in the same note, we are trying to write an expression for AV1 as well as AV2. So let me write AV1 is equal to negative, okay, the output impedance. Okay, now output impedance of first stage. Okay, so we are taking this as AV1 and we are taking this as AV2. Okay. Now, can anyone tell me what is the output impedance of first stage? Let me write this as Z01. Can anyone tell me what is the output impedance of first stage? Can I take the output impedance as 2.2 kilo ohm only, or 2.2 kilo ohm in parallel with the input impedance of first stage? Sorry, second stage. So this is Zi2. This is Zi1. Okay. Anybody can tell me what is the output impedance of first stage? Can anyone attempt?
Resistance parallel with the second input impedance.
Impedance, right, great. So Z01 is not only RC1, along with RC1, here you can see, okay, here you can see, along with RC1, you have a parallel combination of the input impedance of second stage. So Z01 going to be 2.2 kilo ohm in parallel with Zi2, where Zi2 is equal to 15 kilo ohm parallel with 4.7 kilo ohm parallel with beta RA. Correct, Pratibha?
Yes, sir.
Right. So you can find out Z01. So RC1 parallel with Zi2, where Zi2 is equal to 15 kilo ohm parallel with 4.7 kilo ohm parallel with 1.3 kilo ohm. So let us find out what is Zi2. Okay. So Zi2, you will get it as 953.6 ohms. Okay, as I have mentioned previously that I have the answers with me. All what you need to do is just cross-check the answers. Okay, so with which we can calculate Z01. So Z01 going to be 2.2 kilo ohm parallel with 953.6. Okay, so that you will get it as 665.24 ohms. Okay, so AV1 is equal to minus Z01, which is 665.24 divided by RE. Okay, how much did we get RE as? The previous step, somewhere here we found, right? 6.5. Okay, so that is 6.5. So that is equal to 102.34. Are you getting it? So stage 1 gain is 102.34. Okay. So similarly, let's look at stage 2. Stage 2. Okay. Now in stage 2, we shall take the voltage gain as AV2. So AV2 going to be minus Z02 divided by RV. Okay. Now, what is Z02? Z02 is the output impedance of second stage. Okay. Z02. And here it is being clearly given that Z02, okay, is consisting of just 2.2 kilo ohm resistance, right? Because there is no load. In case A, you don't have to connect any load. Only in case 2, you are supposed to take 10 kilo ohm load. So Z02 is nothing but the collector resistance of second stage, which is 2.2 kilo divided by 6.5 ohms. Okay, so that will give you a gain value of minus 338.46. Okay, 46. So you have stage 1 gain as well as stage 2 gain. Therefore, overall gain AVT is equal to AV1 into AV2, which is minus 102.34 into minus 338.46. So for a 2-stage common emitter amplifier, the voltage gain becomes positive because product of two negative values is positive. So that will give you a voltage gain of 34.64 into 10 to the power 3. 10 to the power 3. Okay, so that is the first part. Okay, first part. And output voltage. Okay, so you have calculated the individual voltage gains and overall voltage gain, and then you need to calculate the output voltage. Okay, so this is your overall voltage gain, AV total. You will give some input. So input is given as 25 microvolt. You will get some output. So what is that output? So output by input is basically overall voltage gain, AVT. That implies your output voltage is gain times the input voltage, or 34.64 into 10 to the power 3 times 25 microvolts. So your output voltage is basically 0.8659 volts. So that's your output voltage. First part. In second part, you need to redo part 1 by taking a load resistance of 10 kilo ohm across the second stage. Across the second stage. Okay, so you're going to take a 10 kilo ohm resistance across the second stage. So that means to say AV1 is unaffected, right? AV1 remains the same because you're not connecting anything on the first stage. So AV1 continue to be 102.34. Okay, but AV2 will change. So AV2, let us rewrite the formula. AV2 is equal to minus Z02 divided by RE. And since you are connecting RL value of 10 kilo ohm for case B, okay, let me put it within the cloud, case B. So your overall output impedance Z02 becomes 2.2 kilo ohm parallel with 10 kilo ohm. Okay, so let me come down. So Z02 becomes minus of 2.2 kilo ohm parallel with 10 kilo ohm divided by RE. Okay, so that you will get it as minus 277.42. Okay, so therefore overall voltage gain AVT is equal to AV1 into AV2, that is minus 102.34 into minus 277.42, or overall voltage gain AV total is 28.39 into 10 to the power 3. Okay, so that's your AV total. You can clearly observe that AV total has reduced. In first case, you have had AV total value of 34.64 kilo, and in part B, you have AV total which is close to 28 kilo. Okay, so that's your AV total. Okay, the last part is calculate the input impedance of the first stage and the output impedance of second stage, okay, which is very easy. Part C, you can write input impedance of first stage let's say Zi1. So input impedance of first stage is R1 parallel with R2 parallel with beta RE, that is 15K parallel with 4.7K parallel with 1.3K. So ZI1, you will get it as 953.6. Okay, so that's your first stage. And then output impedance of second stage. Second stage, Z02. So Z02 is equal to RC2 is equal to 2.2 kilo ohm. Okay, this is without RL. Okay, next Z02 is equal to RC2 parallel with 10 kilo ohm. Okay, this is with RL is equal to 10 kilo ohm. Okay, so if you consider a load resistor, you will have your output impedance, which is equal to RC2 parallel with 10 kilo. So that is 1.8 kilo. 0.8 kilo. Okay, so that concludes this particular problem. Okay, so I'll give you a homework. What you have to do is you have to submit me as an assignment. Okay, so homework problem going to be in terms of the H model analysis. All right, fine. So now let me touch the last portion of module 3, part A, which is Cascode amplifier. Or connection. Cascode amplifier, or you can also say cascode connection. So this cascode amplifier is also a multi-stage amplifier. It is also a multi-stage amplifier. The main feature of cascode amplifier is that in first stage, okay, in the first stage, you will have a common emitter configuration. And in the second stage, you will have common base configuration. Okay, it's a multi-stage amplifier. But in cascode amplifier, you will have in the first stage as common emitter and in the second stage as common base. On the other hand, in case of cascaded system, you know, it can be anything. It can be 2 or 3 units of common emitter or 2 or 3 units of common base, so on and so forth. Okay, so now first let me draw the circuit diagram. Okay, circuit diagram. So I've told in the beginning that first stage you will have CD. So you will have a voltage divider bias based common emitter configuration. This is your power supply voltage VCC. Input VI. Okay. Now the output of first stage is given to the second stage, and the second stage will be a common base configuration. So here you will have a common base configuration. This is Q2, second transistor. This is Q1, first transistor. Okay. The biasing resistor RB and bypass capacitor CB connected across. And this is the collector terminal. So collector terminal going to be the load terminal. So this is the load resistor RL. Okay? And across the load resistor, output is observed. Okay, fine. So this is your first stage. CE stage. And this is your second stage, CB stage. Okay. Now, the main feature of common base configuration is that the impedance matching. Okay. So first, what we can do is we can write down the typical impedance values of respective stages. Okay. You know that for a common emitter configuration, the input impedance is high in the range of kilos of ohms. So let me write the input impedance as Zi1, okay, and which is high. So high Zi1 we can write, okay. Similarly, we know that the output impedance of C stage is also high. So you can also write high Z01, okay. Now, if you look at common base configuration, in case of common base configuration, the input impedance is low. Okay, the typical input impedance values, lie in the range of few ohms, tens of ohms. So low Zi2, and the output impedance is very high. So very high Z02. Okay. Now, due to this impedance mismatch, you can see that output impedance of previous stage or stage 1 is high. On the other hand, the input impedance of next stage is low. So this will be in kilos of ohms and this will be in ohms. So due to the impedance mismatch, so the voltage gain, okay, so you can say AV1 is low. Okay, so let me write here, AV1 is low due to the impedance mismatch. Impedance mismatch. And to your surprise, this impedance mismatch is done intentionally. Okay, it is done intentionally. That's because CE stage gives very high voltage gain, and CB stage will also give very high voltage gain. Okay, if the two gains were to be high, then the overall voltage gain, okay, going to be very, very large, okay, which is objectionable. Okay, that's because the overall voltage gain can cause saturation in the output. Okay, I have explained, right, how the saturation takes place. If the overall voltage gain is very high, then there can be, clipping action observed in the output waveform. Okay, so in order to, limit the overall voltage gain, the second stage is being fed with first stage, okay, which will have a higher output impedance. So overall voltage gain becomes AV1, which is low, into AV2, which is high. So your overall voltage gain will be in controllable limits. It will be in controllable limits. Okay. Now, one question: if that is the case, why not second stage directly connected to the source? Okay, you could have directly connected stage 2 directly to the input, right? Why you have to bring this first stage in between? Okay, that's because your common base configuration, okay, will have very poor impedance matching with the input source. Okay, input source you cannot modify. Okay, input can be coming from, let's say, um, you know, it could be a video signal, or it could be some other broadcasting signal. You cannot modify that broadcasting signal just like that, because the setup what they have at the transmitting station is very, very expensive. Okay, just for your amplifier sake, you cannot modify the existing equipment. Rather, you modify the amplifier, because modifying the amplifier going to be the inexpensive affair. All right. So that's the reason, to have a good impedance matching with the source, a common emitter configuration is used. Okay, that's because your, VI normally will have the source resistance in the range of few kilo ohms. So this kilo ohm is going to match with the ZI value of the amplifier stage. Okay, but if you were to connect this source VI directly to the base, emitter of second stage, okay, then you will experience too much of loss of signal, right? Because the source resistance will be in kilo ohm, and your input impedance of stage 2 going to be in ohms. So there will be a huge signal loss, and your output signal may be a distorted one. Okay, so that's the reason common base stage is always fed with a common emitter phase. Okay, and common base allows the following advantages. Okay, the first advantage is high voltage gain. Okay, high AV. And the second, perhaps the biggest advantage, is high bandwidth. Okay, so bandwidth is nothing but the difference of upper cutoff frequency and lower cutoff frequency. Okay, this is your higher frequency, and this is your lower frequency. Okay, so within the bandwidth, the faithful amplification exists. Okay, if I were to compare, let's say qualitatively, the bandwidth of two amplifiers, CE and CB, probably your CE will have a narrower bandwidth. On the other hand, your CB, okay, will have a broader bandwidth. So this is your 3 dB level. Okay. So blue for CB and orange for CE. All right. So you can clearly observe that blue will have wider bandwidth. Okay, the difference between FH and FL is nothing but the bandwidth. On the other hand, if you look at the common emitter configuration, in case of common emitter configuration, you will have a narrower bandwidth. Okay, this is your FL and this is your FH. Okay, so this is going to be the bandwidth of common emitter configuration. So that's how you can qualitatively analyze the bandwidth of two amplifiers. Okay, so since the bandwidth is large, so this particular cascode configuration is widely used in VHF and UHF transmission. Okay, VHF and UHF transmission. So this VHF and UHF transmission are nothing but your video signals. video signals. Okay, so very high frequency and ultra high frequency. This frequency ranges from several megahertz to up to few gigahertz. So that's your video signal transmission frequency. Okay, so your setup boxes will have kind of cascode arrangement within. Okay, because cascode arrangement can handle a very high frequency. All right, so this is the the theory about cascode amplifiers. Okay, there is no analysis as such. So this is what you are supposed to write about cascode connection. For short notes, they can ask.